Hey, today we're talking about cross-function reentrancy, and this is just another type of a reentrancy attack. It's just the variant of the very common single-function reentrancy attack. The principles are still the same. You basically have a function that doesn't follow the CEI pattern correctly, that checks effects interactions correctly, and it basically leaves a window for an attacker or a bunch of attackers to come to your protocol and steal funds away from your contract. So in this video, what I'm going to do is I'm going to walk you through this code where I have got a vulnerable vault right here, and we also have an attacker contract right here. I'm going to walk you through the code, and then I'm going to explain what's going on behind the scenes with some hopefully easy to understand diagrams so that you know exactly what happens behind the scenes, how attackers get hold of the funds, and just basically so that you can understand how to prevent this from happening if you're a smart contract developer in a protocol, or if you're someone just developing their own protocol. It is very important for you to understand all these concepts so you don't get your funds drained from your protocol. Okay, so without further ado, let's get into it. First, of course, we have the license identifier at the top, then we have the pragma solidity, basically stating what solidity version we're using. And just to drill this home, I have imported the Open Zeppelin reentrancy guard, because as we're going to see, we have the non-reentrant modifier in this withdraw function, which in theory should make the function non-reentrant. It does allow the function to be reentrant, not to have a single function reentrancy, or not to be vulnerable to a single function reentrancy attack, because it does have the non-reentrant modifier. However, it becomes reentrant because we are interacting with the transfer function, or better said, the transfer function and the withdraw function both interact with the same variable, which is balances. Okay, and withdraw updates the state of the balances variable in the wrong way, and therefore leaves a window to basically call an attack function or an attack contract on the transfer function and start draining funds from there. But anyway, let's go back to running through the code. We have the vulnerable vault contract, which is a reentrancy guard. Then it has got a mapping called balances, which maps the address of, we could call this user to U into56 amount, whatever, doesn't matter. And then we have a deposit function, which is external payable. And this is just going to allow any user to deposit any amount of Ethereum inside of this contract or token or whatever. It would be nice to have a check in here, but it is for demonstration purposes, so I'm not going to add that right now. Then we have a transfer function. And what this transfer function allows for me to do is to essentially, let's say I have 10 Ether inside of this contract, and I've got a friend who wants some Ether, and I'm a super nice friend, and I just want to allow him to have 5 Ether of mine. I can essentially call this transfer function with my address and my friend's address, and allow him to have 5 of my Ether, or to be able to withdraw 5 of my Ether. Okay, and this will basically update both my balance and, as we can see here, the balance of the message of sender, in which case it will be me. It will basically deduct 5 Ether from my balance, and it will add 5 Ether to my friend's balance. Okay, it's easy as that. And then we have the withdraw function, which is essentially a non-reentrant function, as we've seen before, and it allows any user to withdraw whichever balance they have in this contract. Obviously, this function is not written properly, doesn't follow CEI pattern, because the state update should come before the external call. And that is extremely important, because even if this function is non-reentrant, because we are protecting it with the non-reentrant modifier, we will see that this function indeed allows an attacker, in this case 2 attackers, or an attacker with 2 addresses, to essentially drain funds from real users from inside of this contract. Okay, and then we have the attacker contract, which basically we're going to bring in the vulnerable vault and the address of an accomplice. For this attack, we need 2 addresses. We need an attacker's address, which is going to be the one that is going to deploy the contract. Then we need another address, which can be another smart contract or any externally owned account, essentially. And we're going to need that address to be able to perform the attack on vulnerable vault. And then we have the constructor, where we set the vault and the accomplice. We have the attack function, which calls the deposit function in the variable vault, this one right here, and then it calls withdraw, okay? And then we have the receive function, which is going to get triggered when the withdraw function gets called and it reaches this line here. When call gets triggered, it's going to trigger the receive function of the attacker contract. And then in the receive, if the balance of the attacker contract inside of the vault is bigger than 0, we're going to transfer the accomplice the balance that is inside of this attacker contract, okay? Cool. So let's actually see how it plays out, because it might be a little bit confusing just to walk through the code, but I think when I deployed and I walk you guys through the step-by-step of how to actually perform the attack is going to be much clearer. So we're going to use 4 accounts in this case, okay? We're going to use account 1, and I'm going to use account 1 to essentially deploy the, where is it? Cross function, not the fixed version, the cross function reentrancy variable vault. Here it is. So I'm going to deploy it. Cool. Now we're going to use account 2, and with this account, we're just going to deposit some Ethereum. Okay, let's say I'm going to deposit 10 Ether into this vault, transact, and as we can see in here, we have got 10 Ether inside of this contract. Okay, awesome. So now we're going to, with an account 3, we're going to deploy the attacker contract, and we need to pass in the vulnerable vault address, which is this one, and then we're going to use an account 4, which is going to be our accomplice address, and then we're going to deploy the attacker contract. Cool. So now we have the attacker contract right here, and with the account 3, we're going to call the attack function, and let's just pass in 1 Ether. Boom, perfect, and let's transact. Okay, cool. So as we can see, now the balance of this contract is 1 Ether. But this essentially has created a phantom balance for account number 4. So now if we copy this address and we come into vulnerable vault, we call the balances and we paste in the address of account 4, we're going to see that it has got 1 Ether, okay? Which is bonkers, because the balance of this contract is still 10 Ether. The attacker has got his Ether back, is inside of the contract, and we have got 1 extra Ether phantom, okay? This is not real. The contract believes that the account 4 has got an Ether locked inside of the vulnerable vault, but it really doesn't. The attacker never deposited an Ether. It did momentarily inside of the vulnerable vault, but then it withdrew its Ether and it got it back, okay? So essentially, the contract, the vulnerable vault, thinks that there is 11 Ether inside of the contract, but in reality, it's only 10, okay? And I know it can be a little bit confusing, but bear with me for a second, because now if we go with account 4 and we call withdraw and we transact, it has reverted in here. Oh, because I'm sending, oh, get rid of that. And we transact, we can see that now the balance of the contract is 9 Ether, and we have got 1 Ether. You can see here, the account 4 has got 100.999, so essentially 101 Ether. And the attacker has got his Ether. So essentially, the attacker, or the 2 attackers, have got their Ether back that they deposited into the vault, and they have got 1 extra Ether that they've stolen from the protocol. And they could do this over and over and over and over again, obviously with higher quantities of Ether as well. And let's just do it again with account 3. We're going to call transact. The attacker has got his Ether back. Then we're going to move on to account 4. We're going to withdraw with no Ether value, transact, and boom, it's got 102 Ether up here, account 4. The attacker has got his 2 Ether back, but the balance of the vulnerable vault is going down every time that the attackers attack it. So yeah, it is a little bit confusing if you seeing it for the first time, but let's actually walk through the diagrams so that you could understand how it works, okay? So let's assume the vulnerable vault's balance is 10 Ether, okay? The initial balance is 10 Ether, and just assume that someone has deposited Ether into the contract and it's got 10 Ether, okay? So the attacker will call attack, and then we're going to deposit first, so the attacker's balance is 1 Ether. Then we're going to withdraw, okay? We're going to withdraw, it's going to pass all these checks, and then in the CI violation, we're going to perform the low level call. And in the receive function, it's going to call vault.transfer. So it's going to transfer to the accomplice, okay? It's going to call this transfer function, and it's going to deduct the balance from the attacker or the original account that has called the attack function, and it's going to update the balance of the accomplice, okay? So now the accomplice's balance is 1 ether, but the accomplice never deposited, and the contract's balance is still in touch, is 10 ether, and it essentially created a phantom balance where the accomplice can now drain ETH by calling withdraw, okay? So if the accomplice now, like we saw in the live example in Remix, the accomplice could basically call withdraw, and the accomplice's balance would be 1 ether, so he would get 1 ether from the actual contract, and the contract's balance would decrease. And like I say here, they can just loop this over and over and over again, and essentially drain the contract from funds. Okay, so it is a not very fun place to be if you're this protocol. So how do we fix this? The most important thing, how do we fix this? Just follow CEI pattern, okay? Because even if we use the non-reentrant modifier, which in theory should make a function non-reentrant, and it does, but even if we have this modifier in here, if there is one variable that is shared across different functions, there is a possibility that if you're not following CEI pattern, another function that is not the function where the CEI pattern is broken can become reentrant, okay? Which is exactly the case in this example. So just as a rule of thumb, always follow CEI pattern. It is really, really important. And as we can see here, if we now call deposit, we're going to call withdraw. Okay, we're going to come here. We will have updated the balance of the attacker in this case, okay, correctly. So now it will be 0. So now when we perform the low level call, the bold.balances of address this, so the balance of the attacker contract inside of this vulnerable vault contract is going to be 0, so this doesn't pass the if check, and this never gets triggered. Okay, so now, like I say, the vault.balances address this is equal to 0, and we have essentially prevented the cross-function reentrancy because we are using CEI, and the transfer cannot be called, okay, because this doesn't pass. So yeah, I mean, that was it. It was maybe a little bit intense if you've never worked with the smart contracts before, if you've never really understood what single function reentrancy is. If you don't know what single function reentrancy is or how it works, I do have a video talking about that. It is a little bit simpler, it's a little bit easier to catch if you've not really worked with smart contract before, like I said, or if you don't really know what reentrancy is. So I do recommend you watching that video first, or just reading about reentrancy attacks, single function reentrancy attacks when sending ether, and then come back to the video and go over it again. It is quite a sophisticated attack, and there is another one that is a little bit more sophisticated, which is the cross-contract reentrancy, but we're not going to go into that right now. That will be for probably the next video. I'll talk about cross-contract reentrancy, because it is another type of reentrancy that can be quite common, and they are so much more difficult to catch because we have got a potentially reentrant function, or maybe a function that looks just fine in one contract, but then we have a function in another contract that makes that function be a reentrant, and it's just a little bit of a mess. So I'd rather talk about that on a separate video. But yeah, that was it, guys. I hope you enjoyed the video. I hope this helped you in some way understand how reentrancy works. I am building a GitHub repo with a lot of documentation on different blockchain vulnerabilities and different blockchain attacks. So whenever I have that live, I will put it down in the comment section of the videos, or in the video description, so you can go there, have a look at it, really read through the documentations, see the diagrams, and just get familiar with all of this stuff, because it's really, really important. I do encourage you to basically grab this code. So grab the vulnerable vault contract and the attacker contract, write it in Remix, because I mean, you can copy and paste it if you want, but it is much better if you do write it, because it will stick and it will make more sense if you do write it down from top to bottom and you understand what's going on. So write it down in Remix and just play around with it, okay? So yeah, anyway guys, I hope you enjoyed the video. I will see you in the next one.